Okay, now I want to talk to you about energy conservation and simple harmonic motion. So we started out just like we did all the other areas. We first talk about kinematics, then we talk about dynamics using Newton's second law, and then we do energy conservation. Okay, so here we have the same system. This has a name. This system is called a harmonic oscillator. Harmonic oscillator. That's the fancy name for it. And this is gonna, if we pull this back and let go, it's gonna swish back and forth in simple harmonic motion. If there's no friction on this thing, it'll just go back and forth in simple harmonic motion. And as you might guess, there's an energy associated with this. And if we want to know where this object is going to be, how fast it's going to be going for any position. So like if I said, hey, how about at a over 2, how fast will it be going? Or how about at a over 4, a quarter of the way, how fast will it be going? Well, that sometimes the easiest way to do that is just to say E equals E prime. Now let's call, right when you pull it back, right here, let's call this E. It's got no velocity, it's just got all the energy stored in the spring. So we're going to say that the energy stored in the spring initially, let's say, is 1/2 k times x squared. But x, when you're all the way back there, x is a. So I'm going to say 1/2 ka squared. At any other intermediate time, say like right here, it's going to have a little bit of potential energy stored in the spring. This time that's x because it's not all the way out at A. But it's also going to have some kinetic energy. Okay, so that's the sentence that describes the energy conservation of a harmonic oscillator. We can, since there's a half in each term, we can do things like multiply each term by 2, and then maybe solve for v. Let's do that. Let's solve for v. Okay, so let's get rid of a half, and let me bring this on the other side. So ka squared minus kx squared is equal to mv squared. And then maybe I'll bring the m on the other side and then take the square root. So that's going to give me that v is equal to k over m a squared minus k over m x squared. Okay. And then let's go one step further and factor out that k over m, the square root of k over m. So that's going to be v is equal to the square root of k over m times a squared minus x squared. Let me let you see where that came from. Okay, so let's see how this works. If you want to know the speed at x equals a, let's find the speed when x equals a. When x equals a, it looks like this is going to be a squared minus a squared. That's 0, so v is 0 at x equals a. And that makes sense. It's turning around there. At x equals a, v equals 0. Now, you might also guess that we get the maximum speed then. We'll get the maximum speed when you're not subtracting anything from here, when x equals 0. So at x equals 0, v is v max. And apparently it looks like, if I make that 0, it looks like it's going to be the square root of k over m times a squared, but that I can pull the a squared out. So it's just going to be that. Now, are you recognizing this square root of k over m? Because the square root of k over m, that's omega. And we already knew that the V max is omega a. We already knew that. And the reason we knew that is because if x equals a cosine omega t, remember doing this? Then the derivative of this is a omega sine omega t. And then I put a negative sign there. So we already knew that that was A max. Or excuse me, V max. Hey, since we're talking about A max, we know that A max is omega squared, A omega squared, or omega squared A. And let's just show how that works. Why is that the case? Besides that, if you take the derivative of this, you get a omega squared cosine omega t with a negative sign in front. Well, that's because you get your maximum A when you have your maximum force. And what's your maximum force? Your maximum force is when you have, when it's negative Ka. Negative Ka divided by m. See, this is the biggest the net force gets, negative Ka. And then you divide it by m, and that gives you A max. Now, if you notice something here, the K over m, that's looking like, yeah, sure enough, K over m is looking like omega squared A. Yeah, so you get your maximum acceleration when it's omega squared A. All right, that's what I had to tell you. Thank you. Bye.